had already gone through special forms of the energy equation, right? But we want to resolve another issue. When is a flow compressible, right? So this is a question. Is it just looking at the Mach number 0.3? If above 0.3, then you can now consider the flow compressible, right? So let us look into these matters. Consider a fluid element which is initially at rest. Say an element of the air around you. Okay, it is in the class, you are sitting next to your friend. So consider the air element around you. So the density of this gas at rest is known to be rho naught. Okay, let us now accelerate this fluid element isentropically to some velocity v and Mach number m. Okay, say by expanding the air through a nozzle, right? So we force the air going through a nozzle. So as the velocity of the fluid element increases, because it is going through a confined space, so the velocity pick ups. So the other flow properties will change according to the basic governing equation. So in particular, the density itself, the density denoted by rho of the fluid will change according to the equation below that we have already looked into in our earlier session. All right. So if we look here, a table or a figure, right, for isentropic variation of density with Mach number. So you have the ratio of the density over density naught, okay, from 0 to 1, and then Mach number from 0 to 1, right? So we have a line there, okay, where denoted by 0.3. For Mach number less than 0.3, the variation is less than 5%. Okay, so 5% variation. So at 0.32, somewhere there, okay, you will get a variation, 5%, right? So at low subsonic Mach numbers, the variation of the ratio of density over the density naught, okay, at the stagnation point is relatively flat, right? So there's not much variation. So indeed, for Mach number less than 0.32, the value of the density deviates from density naught by less than 5% for all practical purposes, and the flow can now be treated as incompressible. So you can use the Bernoulli's equation to find the respective values. However, for more than 0.32, okay, for more than this, the deviation is large, right? So if you have the ratio of the density to be larger, okay, so you will get the variation to be more. So as a result, many aerodynamicists have adopted the rule of thumb, and this is why we use a magic number 0.3. Okay, anything below 0.3, we treat it as incompressible. Anything Mach number above 0.3, we then treat it as compressible. Okay. Now, how the ratio of density over density naught affects the change in pressure, okay, associated with the given change in velocity. So the differential relation between pressure and velocity for a compressible flow is given by the Euler's equation. So we have the Euler's equation where change in pressure equal to the negative change in the density times the velocity time the change in velocity. So this can be rewritten as this expression. So this equation gives the fractional change in pressure for a given fractional change in velocity for a compressible flow with local density rho. If we now assume that the density is constant, say equal to rho naught, then you can write this expression where subscript 0 implies the assumption of a constant density. So dividing the last two equations, the one that we seen just now, and assuming the same change in velocity over velocity and pressure, we then have this expression. Okay, you can see that there's expression for the pressure in relation to the ratio of the density. Hence, the degree by which the ratio of density deviates from unity as shown in the figure, right? As we shown in the figure just now, which is related to the same degree by which the fractional pressure change for a given dV over V is predicted. For example, if we have the density ratio rho over rho naught equal to 0.95, and which is occurs at about 0.3, right? Then the fractional change in pressure for compressible flow with local density rho as compared to that for an incompressible flow with different density, density rho naught, will be about 5% different. Let us just quickly look at it. If you have 0.95, okay, let's say this is 0.9, this is 0.95, this is at about 0.32, okay. This arrow should be somewhere there, okay. It's not here, it is exactly at the point of intersection, right? So the variation is only 5%, okay. So keep in mind that the above comparison is for the local fractional change in pressure. So the actual integrated pressure change is less sensitive, okay? So now, consider the flow of air through a nozzle starting in the reservoir, right, at nearly zero velocity. So imagine it is from a reservoir, a big tank, and going through a nozzle. So from zero velocity at standard sea level, right? So you have P naught equal to 2,116 pounds per square feet, and the T naught to be given at 510. And expanding the velocity from 0 to a velocity of 350 feet per second at the nozzle exit. So the pressure at the nozzle exit will be calculated assuming first incompressible flow, then compressible flow. So this is a combination. So according to incompressible flow from Bernoulli's equation, so we know that P equal to P naught minus half rho V squared. So you put inside the number, you will get the pressure to become 1,970 pounds per square feet. For compressible flow, from the energy equation where we know the Cp equal to 6,006 for air. This is, remember, this is in feet pound per slug of degrees R, right? So it's not the normal 1.004 for air for the normal metric equation. So you will then get the temperature, temperature T equal to T naught minus square of velocity over 2 Cp. You put down the number, you get the temperature to become 508.8, right? So putting in the expression for compressible flow, okay, so you will then get the ratio of pressure P over P naught to become 0.9329. Then you will then get the pressure for compressible flow at 1,974 compared to earlier 1,970, right? So there's not much different there because it's about 5%. Note that the two results are almost the same. With the compressible value of pressure is only 0.2% higher than the incompressible value. So 1,974 compared to 1,970. Okay. So we can see here clearly the assumption of incompressible flow is certainly justified because of at very low Mach number. Okay. Note that the Mach number at the exit is around 0.317. It is less than 0.32. Hence, we have shown for a flow wherein the Mach number ranges from 0 to about 0.3, Bernoulli's equation yields a reasonably accurate value. So you can use that. You can use it if it is less than 0.3 Mach number. Another justification for the statement that flows wherein Mach number less than 0.3 are essentially incompressible flow. All right. So let us speed it up a little bit. On the other hand, okay, if the same flow from the same reservoir continue to expand to a velocity of 900 feet per second, right? Earlier, it is only 350 feet per second. But now, it is being accelerated to a speed velocity of 900 feet per second. And repeat the above calculation. So, you will then get the value of the static pressure at the end of the expansion, which is P equal to 1,153 pounds per square feet for the incompressible Bernoulli equation. But when you use the compressible flow equation, you will get a much higher static pressure, okay, 1,300. So note over there, the difference between the two set of result is around 13% different. Okay, so in this case, the Mach number at the end of expansion is already reaching 0.86. Okay, so clearly for such values, the flow must be treated as compressible. So you cannot use incompressible Bernoulli's equation anymore. So in summary, although it may be somewhat conservative, so the author is in this book, Anderson, suggests on the strength of all the above information that flows wherein in the local Mach number exceed 0.3 should be treated as compressible. So less than 0.3, the assumption of incompressible flow is quite justified. So this is for accuracy. Okay, our last part of the today's session, we want to go through the calculation of normal shock wave property. But today we will only going to go through the theory, but we will continue on the examples for calculation of normal shock wave properties in our lecture number 5. Right. Recall the basic normal shock equation. So I have shown this before last week. We have the 5 equations. And number 1 is continuity equation. Then we have momentum equation. We have the energy equation. We have enthalpy equation and the equation of state. Right? So these are the equations that you need to know by heart. So given the conditions, we have shown this as well previously last week. Okay, that in region 1 ahead of the shock, so this is the shock, the thin shock layer, right? You need to calculate the conditions. So given the properties at 1, and then you need to get the corresponding values, right? Examining the 5 equation, this 5 equation, we see that they involve 5 unknowns. We have already gone through this, namely the density, velocity, pressure, enthalpy, and the temperature. Hence, the equations are sufficient for determining the properties behind a normal shock wave in a calorically perfect gas. So we divide. What we need to do now is basically we divide the momentum equation. You take the momentum equation with a continuity equation, right? So divide momentum equation with continuity equation, right? So knowing the expression for the speed of sound A, okay, which is equal to gamma RT, where A equal to square root of gamma RT. So you rearrange that, and then you also have the value of P equal to rho RT. So you can then rearrange that to put inside the expression. So you have you will come up with this expression, right? And use alternate energy equation for region 1 and region 2, right? For region 1, so this is the alternate energy equation. So for region 1, so you express it in terms of the A star, as for region 2, you can also equate it and in terms of A star component, right? From previous, knowing A star is constant across the region because the flow is adiabatic. So put A1 squared and A2 squared values in the equation below, right? So you will then come across this expression. You resolve this, right? Put inside the number which is equal to U2 minus U1, right? And then you rearrange that to make it in terms of the A star component. This is for regroup it. So you resolve this and divide it by U2 minus U1. You take the component on the right hand side to the left, you will get get this expression. So solving for A star squared, right? So you will then get U A star squared equal to velocity at 1 times the velocity at 2. Okay. So if you look here, this equation is called Prandtl relation and can be rewritten as this, where you rearrange it, where you get 1 equal to U1 over A star times U2 over A star. And knowing that the Mach number equal to U over A star, then you can both side times power of 2, okay, you can get this expression, right? For the M2, M star 2 equal to 1 over M star 1. And knowing, okay, where M star 2 equal to this expression, then for both region, you can get that expression. Solving for M2 squared, we have obtained the M2 squared values. Right. Note that this equation is our first major result for normal shock wave. Okay. If we look closely, it states that the Mach number behind the wave, behind the normal shock wave, M2 is a function only of the Mach number ahead of the shock wave. So you can see here, you want to know what is M2, it is a function of M1, right? So this is the case of an infinitely weak normal shock wave. Normally, it is being called as the Mach wave. And furthermore, if Mach number at point 1 is more than 1, then Mach number at point 2 is less than 1, right? And that is the Mach number behind the normal shock wave is subsonic, right? If it is increases above 1, the normal shock wave becomes stronger and M2 become progressively less than 1. However, is in the limit as M1 approaching infinity and the M2 approaches a finite minimum value, which is for air, we will get a value of 0.378, right? Now, let us look into a special case here for other normal shock properties calculation. And let us now obtain the ratios of the other properties. So we want to know what is the density ratio, the pressure ratio, and the temperature ratio across the normal shock wave. So we rearrange the continuity equation. Okay, this is the continuity equation with A star squared equal to U1, U2, we will then have this expression. Okay, so where we know that density ratio at 2 to 1 and velocity ratio at 1 to 2, okay, equal to 1 to 2, and times U1 for both, then you will get this. And knowing this expression, this equation or earlier, then we will get the density ratio, which is equal to the velocity ratio, which is equal to the expression that we have over here. So to obtain the pressure ratio, return the momentum equation and combine with the continuity equation. So we have come back to the continuity equation and the momentum equation. So you rearrange that, you get this expression, then divide with the pressure, pressure at 1, and insert the value of speed of sound squared, which is equal to gamma p over rho. Okay, so knowing again the same thing, A equal to square root gamma RT and P equal to rho RT. So you rearrange that, you put inside this expression, okay, this expression, okay, you can get this equation. From the continuity equation, knowing that the expression here, we can put back at the same thing earlier that we have already looked at this, and we will then rewrite the equation as the pressure ratio, pressure difference in terms of the Mach number component. Simplify the equation to P2 over P1, we will then get this expression. So to obtain the temperature ratio, we use equation of state and say P1 equal to rho RT1 and P2 equal to rho RT2. Knowing R1 is equal to R2, then the P2 equal to rho 2 R1 T2, and just replacing R2 to become R1, where we know that R1 equals to P1 rho 1 T1, then you can rearrange that again. We will get the temperature ratio at 2 to 1 equal to the pressure ratio 2 to 1 times the pressure ratio, density ratio of 1 to 2. Okay, and substitute previous from this equation and this equation that we already found into this expression, and knowing that the enthalpy equal to CPT, right, and CP1 which is equal to CP2, then you will get this expression, where when we look closely, we note that the density ratio, the pressure ratio, and temperature ratio are functions of the upstream Mach number and before the shock wave. All right. Now, going into the second part for some insight of the properties equation. So in the previous properties equation, we have already looked earlier. Okay, if M1 Mach number upstream equal to 1, then the density ratio, I think this is 2, this is 1 and 2. Sorry for the mistake there. I will send back the correction. Okay, and P which is equal to the density pressure ratio P2 over P1, and temperature ratio 2 to 1. Okay, just this one is this one is 1 to 2. Okay, that is, we have the case of a normal shock wave vanishing strength, a Mach wave. Okay, as Mach 1, Mach 1 is the upstream of the shock wave increases above 1, right? What will happen? Okay, so again, this is 1 over 2, okay, and this is 2 to 1 and 2 to 1. Progressively increase above 1. In the limiting case of Mach number 1 approaching infinity, okay, the equation give the below condition if for air gamma equal to 1.4, right? So let us look at what happened. How about Mach number is less and equal to 1, the subsonic case, right? So normal shock wave does not occur in subsonic flow. However, on a mathematical basis, this equation allow solution for M1 less and equal to 1, and this equation embody the continuity, momentum, energy equation, which is in principle, and do not care whether the value of M1 is either subsonic or supersonic. So here is an ambiguity, which can be only resolved by appealing to the second law of thermodynamics, okay, where we know that the change in the entropy, the S in irreversible, is which more than equal to zero, and where we recall back the second law of thermodynamics, which determine the direction which given process can take. Let us apply the second law to the flow across a normal shock wave and examine what it tells us about allowable values of M1. All right. So knowing from the previous entropy, equation for a calorically perfect gas, both the gas constant R and specific heat at constant pressure are constant. So we know we can then write back the entropy equation as a function of the temperature ratio and the pressure ratio. First, we consider the entropy change across the normal shock wave. And knowing this expression for the pressure ratio, and then inserting it in the equation, rearranging it, we can then substitute the equations into entropy. We have this expression, and the entropy change from 2 to 1 across the shock is a function of the upstream Mach number only. And the second law dictates that the difference between the entropy at position 2 to 1, which is more or equal to 0. So if Mach number at 1 equal to 1, S2 equal to S1, right? And if Mach number at 1 more than 1, then S2 minus S1 is more than 0. Both of which obey the second law of thermodynamics. However, if it is Mach number at station 1 is less than 1, then it gives S2 minus S1 less than 0, which is not allowed, okay, by the second law. Try to appreciate that. Consequently, in nature, only cases involving Mach number more than 1 or equal to it are valid. Okay, that is, normal shock wave can only occur in supersonic flow. That's why it cannot occur at subsonic flow. All right. And then finally, we go to the last part, and the total normal shock properties calculation. And let us now obtain the ratios of the total condition properties, P02 over P01, the pressure at 02 and 01, the temperature ratio at 02 and 01 across a normal shock, right? So again, I put up back the figure there so that we can appreciate what's going on. To help us calculate this condition equations, we consider this particular figure, which illustrate the definition of total condition ahead mean at station 1 and behind the shock wave. So we put also the entropy there, S1 equal to S1A, S2 equal to S2A when the flow is isentropic. Okay. Right. Knowing energy equation, enthalpy equal to CPT, as well as this expression, so we can then replace the component there and recall the definition of previous total temperature, which is T0, and consider point 2 is the stagnation point where velocity at 2 equal to 0 and T2 equal to T0. Then the previous energy equation can be written as, so this energy equation, it can be written as this. We have already seen this just earlier. Then we can state the equation as follows, where we have Cp T01 equal to Cp T02, where Cp is constant, then T01 will be equal to T0, 2. And the total temperature is constant across a stationary normal shock wave. All right. So total pressure, P02 over P01 can be derived from the entropy equation, okay, as follows. To examine the variation of total pressure across a normal shock wave, written equation above and between the imaginary states 1A and 2A. So you have then replace S2 to become S2A, S1 become S1A, and you as follows. From the figure, we have the following, right? Following condition for entropy, for the temperature, as well as the pressure. And thus the equation can then be written as follows, right? In terms of the component of 0, 2 instead of 2A. Right. So we have already shown that T01 equal to T02 equal to T01. And the equation of the entropy different can be rearranged. And we know that S2 minus S1 is more than 0 for normal shock wave. Okay. It cannot be less than 0. Okay. Hence the equation states that the pressure at 0,2 is less than pressure at 0,1. The total pressure decreases across a shock wave, right? So when the flow across the shock wave, the total pressure P0 at 2 is obviously less than P0 at 1. So in summary, we have now verified the qualitative changes across a normal shock wave for pressure P2 over P1, for the density rho 2 over rho 1, and temperature, and we have the Mach number at 2, and T02 over T01 and P02 over P01 are functions of the upstream Mach number M1 only. Okay? Right? So to help obtain a stronger physical feeling of normal shockwave properties, so this particular figure has already been plotted by researchers that showing as a function of Mach number upstream, M1, before the normal shock wave occur. So by having this table, it's much easier to figure out what is the corresponding value for Mach number 2, okay, and what is the corresponding value for, this is for M, for Mach number, and this is the variation for the PO2 over PO1, and this is the variation for P2 over P1 for different Mach number, and for variation of T2 over T1 and density 2 over density 1, right? So with that, we will continue. Continue the examples. Probably through examples, we can then appreciate what is the theory behind it. So we will look at a few examples. If you would like to go through the example by yourself, you can look into the examples in the Anderson book at the chapter number 8. Right, so you just continue on the topic of calculation of normal shockwave properties. There are a few examples that we are going to go through together next week.